This is Steve Edford again. I want to talk about special relativity this time. And I want to tell you about how it's actually not so special. So what I'm going to do is dissect it, but I don't feel like putting it back together again because it wouldn't be worth bothering with. Okay, first of all, one of the things that special relativity says is that when an object approaches the speed of light, the closer it gets to the speed of light, its mass increases toward infinity. Okay, now this doesn't happen because actually it's happened once, but it didn't happen. So I got some numbers here to show you. So this is 1969, the Apollo 11 mission, the one that went and landed on the moon. Okay, so the mass of the entire ship was 43,500 kilograms. The velocity to achieve orbit was 17,500 miles per hour. According to the Lorentz transformation equation, the change in mass would have been 5.5 kilograms. That means it increased by 5.5 kilograms. And that doesn't mean that you put a 5.5 kilogram chunk of mass on it. It means that everything on the ship and everything in the ship increased in mass, including the astronauts. Unknowing of it, their mass increased a certain percentage also. But anyway, this mass doesn't come from nowhere, because otherwise it violates E equal mc squared. You have to have energy to get mass from it. And the amount of energy it would take for this 5.5 kilograms of mass would be 4.94 times 10 to the 17th joules. Give you an idea how much energy this is. The nuclear bomb they dropped on Nagasaki, Japan in World War II, the energy it would take 5.6 of those bombs to get that much energy. Now I know Apollo 11 wasn't carrying that much energy with it when it went to the moon, and besides, it wouldn't matter even if it did, because we do not possess the technology to convert energy into mass. That's the kind of process that happened in the Big Bang, when energy converted into mass. So anyway, that's just something that it never happened. Objects do not increase in mass to that extent. So there's another thing I wanted to mention too. I've heard before that people would say that if you're in a rocket ship and you're accelerating toward the speed of light, that your ship becomes infinitely massive, so that now you don't have enough fuel to accelerate any further. That's why you can't reach the speed of light. Well, this is actually wrong, because when you're on a ship and you're traveling near the speed of light, you carry your fuel with you, and fuel has mass. So when your ship becomes infinitely massive, so does your fuel supply, so does your rocket thrusters. Everything increases in size and mass. So you got plenty of fuel to accelerate further. So that one doesn't work either. So then, now we have the situation where they supposedly proved time dilation was when they took two cesium clocks. One cesium clock stayed on the Earth. The other they put on a satellite in orbit around the Earth. Well, over a little time, these clocks got out of sync, probably by a few nanoseconds, and they proved that proved time dilation. Well, I would say no, it doesn't. It proves clock dilation, because the cesium clock does not manifest the flow rate of time. They're not linked together. Just because the clock measured time at a different rate doesn't mean time passed at a different rate. That's an assumption. So anyway, if these two clocks got out of sync, over time they'll get more out of sync. Let's just say they get out of sync by 1 minute. So now, all right, well, first of all, back up a little bit. That they claim that cesium clocks are so accurate that because the cesium decays at a constant rate and it never changes. Well, that's where they're actually wrong, though, because they've already proven that it can decay at a different rate, because that's what happened with the cesium clock on the satellite. is that the cesium decayed at a different rate, and that's why it measured a different time. They've already proven it. But you'd say, wait a minute, no, that we know everything about nuclear physics. We know that can't happen. Cesium always decays at a constant rate. Well, apparently not, because here's the problem. When you think you know everything about something, you cease to learn anything else new about it, because what else is there to learn if you know everything about it? So what I've learned about nuclear physics is that, well, cesium can decay at a different rate. They didn't learn about that because they think they already know everything about nuclear physics. Well, they were kind of wrong there. But anyway, here's another point too on that. This clock that's on the satellite, if it gets far enough out of sync, like say as much as a minute, it's off by 1 minute now. All right, now the cesium clock, I believe when it's in orbit, it's running a little faster because time always runs slower on Earth. So it's running a little faster. So now this cesium clock, which is on the satellite, if the cesium clock is 1 minute into the future, actually in the future, not just reading that time, but it's actually in the future. So is the satellite. So the satellite has disappeared. And you can't see it now because it's in the future. But you'd say, well, wait a minute, you can see the satellite from the past. Well, yeah, you can. You can see the satellite from 1 minute before, but it reads the current time. It doesn't read future time. So I would say that if you look at that clock on the satellite and it reads the future time, but you can see it right now, it's not invisible, it hasn't time phased out of the present, then the clock is just reading the wrong time. So that's about all there is to that. All right, now another one is, I saw this one when I watched a TV series on A&E called Genius, where season 1 consisted of 10 episodes about the early years of Albert Einstein. Well, one of the times in there, he's walking through the village square, and he looks at a big clock on a building. And so that's when he conducted his famous thought experiment. He imagined that if he could race alongside a beam of light, that time would stand still. So he jumped right to his conclusion. He didn't put any thought into his thought experiment. So I'm going to do that for you. Okay, so to set this up, here's a little something that you could probably have some fun with this at a local bar or something. You could make a bet for a beer or whatever. Okay, there's two guys sitting in a basement with no windows in it. The first guy asks the second guy, "Can you see me?" The second guy says, "Sure, I can see you. You're right there." First guy says, "No, you can't." Second guy says, "Of course I can. You're right there." So the first guy, he reaches over and turns the light out. And he asks the second guy, "Can you see me now?" The second guy says, "Well, no, I can't see you now." The first guy says, "Well, that's because you never could see me. You could only see an image of me, and the image is carried by light. If there's no light, there's no image." So that's the point there, that we all think that we're walking around looking at reality when really we're looking at an image of reality. And when you see things that are moving, it's like a film strip. You're seeing things actually a frame at a time. It's image after image coming into your eye. So now if you imagine what's going on with this clock, you're racing alongside the beam of light. Now alongside the beam of light, there's a film strip that's going along. It's a film strip of those frames of images of the hands on the clock. And you're racing alongside it. All right, now, one thing that works out fairly convenient for this is that I found out that light travels within about 97.5%, that it travels about 1,000,000,000 feet per second. So we'll just use that. So now this film strip is coming at you at the speed of light. So each frame of the film is 1 foot long, and the film is coming at you at 1,000,000,000 frames per second. So that's what you're seeing if you're standing still. Now, if you're racing alongside this beam of light, you're also racing alongside this film strip. So you're seeing that one frame on the film over and over. You see the same frame. So that's why it seems like time is standing still, because the second hand on the clock is not moving. But it's an illusion because you're not seeing the actual clock. You're seeing an image of the clock. It's easy to have illusions and mirages with images. But of course, now you'd probably say, yeah, but the problem is that light always travels the speed of light relative to the observer. Well, now, if this is true, if I'm racing alongside alongside this beam of light at the speed of light, then light has to speed up, I guess, and it keeps up with me. So now it's coming at me at the speed of light. Well, now the second hand on the clock is moving at normal speed. So there is no time dilation in that case. Now another way to look at that too is like, as you find out your buddy that stayed back by the building while you're traveling the speed of light and seeing the hands on the clock not moving, you get back, your buddy's going to confirm to you that, well, the hand on the clock moved the whole time you were gone. It didn't change any. So now what you can do is you turn around and you come back at the speed of light the other direction. Now this film strip is coming at you at twice the speed of light. So now the hands on the clock are moving twice as fast. So that by the time you get back to where your buddy is, your clocks are going to be back in sync, seemingly, because you just saw an illusion. You didn't see when time was really passing like that. So now there's another one I want to talk about. It's kind of an old one. It's called the twin paradox. You probably heard this one before. You have two twins. One stays on the Earth, and the other gets on a rocket ship, and he travels out real far and real fast out into space. He's gone for a while, and he comes back, and his twin that stayed on the Earth is dead and gone. They've already buried him. But he's still young, though, because he was traveling, and according to Einstein, time travels real slow when you're traveling real fast and real far. Well, the problem with that is that, what if you reverse it? What if you say that the twin on the Earth is the one traveling, the one on the rocket is not traveling? Well, of course, they always try to say, well, it's not a paradox, because if you look at it that way, because we know that the twin on the Earth is not moving. The Earth doesn't move. Well, that's not true, because we know that the Earth does move. It orbits around the sun. The solar system is moving through the Milky Way. The Milky Way is moving through the universe. All this, the solar system is moving through the Milky Way. The Milky Way is moving through the universe. Everything's moving. But so, and another thing, here's the key to it, that they're violating Einstein's rules, because Einstein said that any inertial reference frame is equally valid and none can be singled out as preferred. And that's exactly what they're doing. They're singling out the earthbound twin as their inertial reference frame. They're giving it preference, that's the one that's not moving. Well, what if it turns out to be that while they're both on the Earth, one twin's on his rocket, and you're actually moving through space at a certain velocity, like say to the right. Now the twin on the rocket, he gets on his rocket and heads off to the left, the other direction, at that exact velocity. Now what you actually have is the twin on the rocket is actually sitting still in space, but the twin on the Earth continues to move like they were before. So now the twin on the Earth is actually moving less than the one in the, he's moving more than the one in the rocket. So he should be the one to stay young. The one on the rocket should age. See, so it is a twin paradox. But anyway, like as usual, everybody can go on year after year arguing about it, debating it over, whatever. That's just a different perspective on it. Now here's another one I wanted to cover. It's the difference, it's this thing they call the fabric of space-time. Okay, what I always wonder about that is the fabric of space-time. I guess that's space-time. And I always wondered, like, what kind of units would that be? Because space is cubic meters, time is seconds. So space-time, is that cubic meter dash second? It's kind of an odd unit to use. I wonder how that would fit into an equation somewhere. But now here's something that there's a difference between space and time. They're not the same thing. So here's the difference. This is something important to keep in mind, is that space is something that we move through by our own will at our own rate. Space has no control over us. But now time, on the other hand, we do not move through time, but time moves through us by its own will at its own rate. We have no control over time. See, it's just inverted around. And not only that, but space is something we move through the three axes. East, west, north, south, up, down, all directions like that. But time doesn't move in a linear fashion like that. I would think that, I mean, I could be wrong, but I imagine that time emanates from within and emanates outward. That's the way time flows. Because it would make sense, because if you're way out in space and you're looking back at the Earth with a telescope and you're watching things moving on the Earth, that video feed that's coming at you frame by frame, when something happens on the Earth, the sun shines on the Earth. It reflects off the Earth, and it carries that image out in all directions from the spear-shaped Earth. It carries the image in all directions, emanating from within and emanating outward. See, that's the way time flows. That doesn't matter so much. The important thing is that there's a difference between space and time. That they don't mix together. But anyway, that's probably about it. There's probably some things I forgot about that, I don't know, maybe they're not that important or something. But anyway, that's about it for special relativity. Maybe I'll come up with something else later. I got a few things in mind. I want to do one video later on evolution, because I got some key evidence there. And I won't do what they expect, using the Bible to argue against evolution. I'll be using science. Yeah, science argues against evolution, if you can believe that or not. I've got the information on it. Anyway, another one. I've done some other stuff. I did some things on math, on coming up with the same thing I come up with. It's called the sum of digits, to where if you use it with base 10, the number 9 is a magic number. Well, I found out that it's also the same way with other number bases from base 2 through base 36. They all exhibit the same behavior. But anyway, more of that later. So anyway, later on sometime.